Hi guys, today we're going to learn how to compute the volume using the disk method. Now, if we revolve a figure about a line, okay, a solid of revolution will be formed. The line is called the axis of revolution, okay? The simplest such solid is a right circular cylinder, or what we call a disk, okay? So let's say that you have this equation, this is your function, okay, and you're going to create like a rectangle. Imagine that you have your Riemann sums, okay? What you're going to do with this rectangle that you have over here is you're going to rotate this and it's going to come out of the paper, okay? And you are going to form this disk that you see. The rectangle that you are seeing here pretty much is represented with this situation that you see here, okay? So it's forming this disk that you see over here. This disk is a representation of what it's happened infinitely many times from here to here. Here in 2D, you would be here seeing that it's from A to B, okay? So this is what it's happening infinitely many times. Usually what we do to represent the axis of revolution, we put a little arrow here so you can see that which is the axis that you are revolving. You can revolve around the x-axis or you can revolve around the y-axis or lines, okay? So what we have here is that to find the volume of the solid, what we're going to do here, okay, as you can see here, we're going to partition it into rectangles, okay, like Riemann sums, which are revolved about the axis of revolution, in this situation the x-axis. Okay, so what you form is something that looks like this, okay? So as you can see, this is a disk, okay? So each disk is a thin cylinder, very thin, okay? It's almost like a piece of paper, as thin as that or more, standing on its side, okay? So you know from geometry that the volume of any cylinder is going to be pi r squared h, okay? So the volume of this disk, okay, that you see here, let's label it. It's going to be this height that you see here, okay? It's going to be your r, okay, your big R. Actually, that height is going to be the radius. And then what you have here is going to be the height, okay? What we in geometry, you were calling it the height. We're going to call it, since we are in calculus, delta x. It means the change on x. Why on x? Because it seems that this is the x-axis. So representing this as calculus, okay, so we have the pi, then you have the r, okay, this r is going to be with x, r of x squared, and then your height is going to be the delta x, okay? So you can see that this delta x is pretty much screaming the dx that you have for the integral, okay? So adding the volumes of all the disks together, you know that the approximation of the volume of the solid is going to be the summation from, let's call it k equals 1 to n, okay? As many n's that you want, you can tend the n to infinity actually, okay? So you are going to have that it's going to be pi times r of x, okay, square, okay, times each delta x, that each delta x is indexed with this, you have as many as this, okay? So this is indicating that you are adding infinitely many, or n in this case, cylinders, okay? To get the exact volume, you can imagine that we're going to take the limit when the limit of that n approaches to infinity. So you have the limit when n approaches to infinity, or in another way you can do when the delta x, you can also represent this when delta x approaches to 0, meaning the slice is so thin that you can barely see it, okay? You can do that. Either or would work, by the way, okay, in case that you are wondering. So this is what you have. So the formula that we're going to learn today, okay, it comes from this idea, okay? Obviously, this is kind of like the notation that you didn't like as much before with Riemann. So the more user-friendly notation that we're going to have here is the volume about the horizontal axis by disks. Please note that it's a horizontal axis, is going to be the volume is equal to pi, okay, and this pi is not magical, comes from this pi. The integral from, let's say, a to b, okay, those are going to be x values of the r of x square, and then you have the dx. Remember that the delta x is technically speaking your dx. Do you see it? Now, what's the difference between horizontal? Okay, this is what we have, horizontal. Okay, the volume about the horizontal axis. Now, if you have the volume about a vertical axis by disk, what you are going to have here, okay, since it's vertical, you are going to be working with y's. Therefore, you have from A to B or C to D. Okay, what you know is that this is y1 and y2, and then you have r of y squared dy. Okay, so you can see that it's very important about the volume about either horizontal axis or vertical axis. If it's horizontal, it's going to be with x's. If it's vertical, it's going to be y's. Okay. So what you know here is that the disk method can be extended to cover solids of revolution with a hole in them, and this is what we call the washer method that we're going to see in a bit. Okay, so I think tomorrow. Okay, but let's see the formula so you can see it and have it handy here. If it's a washer method, we call it washer because, as you can imagine, washing machine. Okay, so it's hollow inside, right? So you are removing instead of like, if you have this, you are removing cylinders inside. So that's why we call it a washer. It's not because we're super original. Okay? So what you're going to have in this washer method, you're going to have an outer radius, or the big radius. That's why it's with capital R. And you're going to have an inner radius that is going to be with small r. Okay, so what you have is that the volume about the horizontal axis via washers is going to be pretty similar to this one. Look, you have the pi, then you have the A and B. Okay, then what's going to change here? Well, what you're going to do is you have your big R of x, okay, square, and then you're going to remove the little r of x, okay, to that one. So you're going to have a hollow situation. Do you see it? Okay, so you compute this volume and then you remove this volume from the inside. Okay, as you can see, horizontal axis, again, you're working with x's. If you have the vertical axis in this situation, you are going to be working with y's. Okay, so what you have here is square minus, and your little r is going to be square, and then you have dy. Do you see the difference here? Okay, so several things that you need to remember, okay, to have all these formulas handy so you can use them without even memorizing them, just by remembering them, okay, what they mean. In the disk or washer method, the representative rectangle is always perpendicular, okay, to the axis of revolution. Okay, so if your axis of revolution is the x-axis, it's going to be like this. Okay, if the axis of revolution is the y-axis, then it's going to be the opposite way. Okay, so if the representative rectangle is vertical, you will work with x's. If the representative rectangle is horizontal, you are going to work with y's. I will call it that. So there are some great examples using GeoAlgebra that can help you to visualize this situation. Okay, I'm sharing that with you in Schoology. Okay. In this example, they tell you that R is the region in the first quadrant, so please note that it's in the first quadrant, bounded by the graphs y equals 9 minus x squared, x equals 0, x equals 3, and y equals 0. Okay, so the first thing that you're going to do is draw that. Okay, so let's graph the situation so you can see what's the business here. Okay, so we have that the vertex here is at 9. Okay, so we have a situation that looks like this. Well, my graph is not very beautiful, but you can use your imagination there. Okay, so you can see that here, okay, at x, this is going to be x equals 3, and then your x equals 0 is here, and sorry about that I did it a little bit ugly. Okay, and then y equals 0 here. Okay, so you have that this is going to be your x-axis. Okay, so this is going to be your x-axis, horrible handwriting there, and this is going to be your y-axis. So the part that you are interested here is going to be this shaded region. Okay, so that's what we have here. Now, in addition to that, let's keep reading. Set up the integrals needed to find the volume of the solid formed by revolving R about the indicated axis. In A, they are asking you about the x-axis. So they are telling you that this is your axis of revolution. Please note that your axis of revolution is going to be that one. Meaning, let's see. Okay, so this is your axis of revolution. Okay, so what do you have? The first thing that you need to do is you have that this is the point, well, this is the point 0, 0, obviously. This is going to be the point 0, 9, and over here you have the point 3, 0. Okay, so you have those intersection points. They are very beautiful. About the x-axis, this is telling you that you are going to have your representative rectangle perpendicular to the x-axis, meaning you are going to have a rectangle here. Okay, This is going to be your representative rectangle. Do you see it? That's your representative rectangle. Let me draw it here. That's your representative rectangle. You can draw it in any part of the orange area, okay? So what do you have here? About the x-axis, you are going to use, you can see that there's no hollow situation here, there's no holes here. It's actually all the orange part is attached to the axis of revolution. Therefore, you are going to use the disk method, okay, for this one. Okay. In addition to that, here we're going to be working with axis, with x, because you have to work with the x-axis, meaning horizontal axis, so we're going to be working with x's. So the first thing that I ask you to find here is the radius, the big radius. For finding the radius is this, the distance between this, okay? So you have that the top of this one is going to be the equation that it's a quadratic function. So you have that it's going to be 9 minus x squared, and the bottom is going to be y equals 0, so this is going to be your r of x. So you can see that r of x is going to be 9 minus x squared. Once you have that, what are we going to do? You are going to use the formula that we just covered, okay? So it's going to be the volume is going to be equal to pi, because it's part of the formula. The integral, now you're working with, remember, x's. So if you're working with x's, it's going to be from 0 to 3, okay? And then you have that it's going to be 9 minus x squared dx. You're going to tell me why this is square. Remember that it's radius square, so this is your radius and this is square. You might tell me why you have this, because this is changing depending on where you are positioned in your x-axis. That's why this is going to be your situation. So for part B, what we have that changes, you have exactly the same orange area as you can see, because we share the same hypothesis of the problem. The only thing that changes is now the axis of rotation. Now you're going to rotate this situation about the line y equals negative 2. Where is that? Okay, so let's assume, or let's label here our graphs. You have that this curve that we have over here is the quadratic function 9 minus x squared. Then this one that you have here, vertical, is x equals 3. This is x equals 0. This is y equals 0. And then you have that your axis of revolution is here below. Okay, so let's say that that is going to be your y equals negative 2. So that's your axis of revolution. Let's do it with a highlighter so it's pretty clear for you that that's your axis of revolution. As you can see, I always indicate the axis of revolution. Now, the issue that we have here, just visually talking about the situation that you have here, is that you do have a hole. When you rotate this, you are going to have like a rectangle, and the rectangle pretty much starts from the axis of revolution. So your rectangle, okay, wherever you want to draw it, but I'm going to draw my rectangle here, okay, it needs to be on the orange area. So you can see that it's too tall. Do you agree with that? It's extremely tall. So this rectangle from here to here, it's going to be big R. What's going to be little r? The hollowness here. So it's going to be a rectangle here. Are we okay with that? So the first thing that you need to recognize here, this is a washer. Why do you have a washer? Because there's a hole in between the axis of revolution and your area that you are rotating. Remember, you are rotating this. Imagine that it's coming out of the paper here, and you're creating a disc. Okay, so you do have a hole. Okay, so the first thing that I would always do is big R of x. Again, you have that it's perpendicular to basically an horizontal axis. Therefore, you are going to be working again with x's. Okay, so that's another thing that you need to recognize. This is your axis of rotation. Therefore, perpendicular. You are going to do top minus bottom. I'll work with that because you have the x. Now, the first R is going to be this one, the big one that you see here, from here, technically speaking, from here to here. And your top here is going to be the quadratic equation, so it's going to be 9 minus x squared. And your bottom equation is going to be this, the negative 2 is minus 2. So technically speaking, this big R is going to be 11 minus x squared. You might tell me, why are you getting that crazy 11? 9 plus 2, that's going to be 11. So that is the value, wherever you're changing here, of this big R. Now, what is going to be little r? Little r of x is going to be this one that you have here, the height of the radius of the hollow, okay, or of the hole that you have, of the hollow situation that you have in the disk. So top here is going to be 0, and then your bottom is going to be again negative 2, so it's minus minus 2, so little r is going to be just 2. So when you set up your integral, is going to be b is going to be equal to pi integral, and then you have big R, which is going to be 11 minus x squared minus small r, that it's just going to be 2 squared, and all of this dx. Now the question is, you're going to tell me, are the limits of integration changing? You tell me, do you see that the x's change from here or here? No, the x's are the same because we're working on the x with the x's. Everybody happy with that? So you have that for the washer. So for part C, what we have is that the axis of rotation changes. Now it's going to be the y-axis. So you have here your axis of rotation, okay, indicate that we are rotating, okay, so you have your equations here. You have that it's x equals 3, x equals 0, y equals 0, and then you have that the parabola here is going to be, what was it, y equals 9 minus x squared. The great part about this situation is that you have the same graph. Now, about the y-axis, what's the difference here? The y-axis is telling you that you're going to be working with y's. Okay. Another thing that you can see is your representative rectangle is going to be perpendicular to the y-axis. So that's your rectangle. Okay. So let's draw it there. Okay. So now we're going to be working with right minus left. Now, what are you going to do in this situation? A disc or a washer? In this situation, what you're going to be doing is going to be a disc. Why? You don't have a hollow. When you rotate this, okay, this rectangle along the y-axis, you are not going to have anything, a hole in the between. Okay, so this is going to be a disc. Okay, so what do you have here? Your big R of y is going to be equal to right minus left. Okay, the right situation here is going to be the curve. Okay. The issue with this curve is that it needs to be in terms of y and it's in terms of x. So we need to solve, okay, so pass the x to the other side, so you have 9 minus y, okay, and then you have that because we're in quadrant 1, I know that it's plus minus, but you only have x is equal to square root of 9 minus y, okay. So you do have that it's going to be 9 minus y because we're working with y's, okay, please remember that we're working with y's. And then your left, what's going to be here? Your left technically 0, so your r of y is going to be just the square root of 9 minus y. Do you need the 0? Not really, but I'm showing you so you know the right minus left, okay? So this is going to be your radius. Now we're going to apply the formula. You know that it's going to be the volume, and then you have pi integral, and then what's going to be the integral. Here, watch out, okay? The limits of integration are not going to be the same as before. Why? Because we're working with y's. With y's, what do you have here? Well, you start here at 0, right? But you're going to end up here at the top. What's this at the top? Well, you know that since you are working with the equation y equals 9 minus x, this is a point 0,9, so the highest point on the y-axis is 9, okay? So please note that that's going to be different because it's always working with y's, okay? Now, you have the square root of 9 minus y, and all of this is going to be squared dy, and that's going to be your expression for part C, okay? So you can see that it's very different, okay, depending on the axis of rotation. Now, let's do another situation. If I tell you to rotate the same problem, but about the line x equals -2, what do you have? What you have is you're going to have a vertical line over here as your axis of rotation, okay? Let's say that that is x equals -2, okay? So this guy over here is your axis of rotation, and what we see is that my representative rectangle is going to be here, right? Okay. So the problem of this representative rectangle, okay, is that it has a hole in the middle. So you can see that this is a washer. In addition to that, immediately you can see that you are going to be working with y's, okay? So it's a very similar situation as before, except now it's washer, okay? So it's going to be a situation where you do right minus left, and you're going to be working with y's. Okay, So your big R is going to be the top of the orange situation is going to be the curve, which we already discovered that in terms of y it was this one. So your right is going to be 9 minus y, and your left here is going to be the yellow, aka the axis of revolution, which is going to be x equals -2. So you have that it's -2. So what you have is square root of 9 minus y plus 2. Do you agree with that? So this is going to be your big R. Since it's a washer, you also have a small r, which is going to be the hole, okay, the height of the hole. Okay, so they are going to be the representative rectangles that basically create the hole. So you have that little r of y is going to be equal, right minus left. The right part of that hole is going to be the axis, okay, the y-axis, as you can see here, or x equals 0. Okay, so it's going to be 0 and minus, okay, what's going to be on the left here. The left is the axis of revolution, which is -2, so you have that this is 2. Okay, so what you have here is you have that the volume is going to be equal to pi integral, okay, and what are going to be the limits of integration here? Your limits of integration, again, they are going to be based on the y, so you know that this is the point 0,9 and this is the point 0,0, okay, and this is the point, what's that, 3,0, so you know that it's going to be from 0 to 9. Why? Because that's the lowest part of the orange part and the highest part is 9, okay, so that's why, because you are based on the y's. And then you have that it's going to be big R, okay, what's big R? Root 9 minus y plus 2, all of this square, okay, and then you have that it's going to be minus 2 square and all of this, okay, dy, and that's going to be your situation. As you can see, it's very important, okay, let me put the 4 problems here. The axis of revolution, here we have the same setup. The hypothesis and the shaded region here is the same. However, in this A, B, and C and D, we're changing the axis of revolution, and that will give you an entire different situation, okay? So the last example of the day, they are asking you to find the volume of the solid formed by revolving the region bounded by the graphs of y equals 2x minus x squared and y equals x squared about the line y equals 3. Okay, so let's graph them. Okay, so what you have here, you have a parabola. Okay, let's start with this one because it's a parent function. So you have a situation that looks like this, right? So this is y equals x squared. Then you do have a parabola that it's facing down. Okay, so the vertex is somewhere here. What we know is that it intersects somehow here. Okay, so you have a situation that looks like this. Okay, and that's what we have. Okay, this is the other parabola, and actually you can do it like this. Okay, even though I put an arrow there, let me erase that arrow so it's not confusing you. Okay, so somewhere there it's a vertex, right? Okay, so that's what we have. Okay, now about the line y equals 3. Okay, the line y equals 3, where is the line y equals 3? The line y equals 3 is going to be further. Okay, so let's draw it somewhere here. Okay, so it's far away. Okay, y equals 3. Okay, so that's your line. Okay, this is going to be your equation y equals 2x minus x squared, right, over here. And the area of interest for this situation is going to be this one. So it's the purple area, and your axis of revolution is going to be over here. Okay, so you are clear. You can see what's the business here. So you're going to tell me, how in the world we know the points of intersection? Well, to find the points of intersection, what are you going to do? You are going to take a little trip to Algebra 2. Okay, your Algebra 2 resources are always useful. You are going to set your two equations equal, which is not that bad. Okay, you are going to solve for x. Okay, solve for x. What happens here? You do have that this expression, what's going to be this expression over here? So you have that it's 0, and it's going to be what? 2x squared. Okay, minus 2x. Okay, so what you can do here, okay, if you want, you can take a common factor, the 2x. So you have that it's going to be x minus 1. Okay, So what do you have here? Your solutions are 0. Okay, so you can see the one that we have here. Okay, that I pretty much did it by guesstimation there immediately as I saw both, but that's the 0 that we saw there. And then you have the 1. Okay, so we do know that this is going to be 1 something. Okay, so I'm going to write them there. That's what we have. Now, keep reading here about the line y equals 3. The line is horizontal, meaning what do you have here? We're going to be working with x's. Okay, so that's going to be the variable that we're going to be working with. It means that it's going to be top minus bottom. But also you need to decide, are we doing washers or discs here? Clearly you can see that there's a humongous hole here between the axis of revolution and the area of interest, that is the purple zone. Okay, so this is going to be a washer situation. Let me put it here. We are doing washers. Okay, so it's clear for you what formula to use. So after that, what do you need for the washers? For the washers, we do need, okay, a big R of x and a small R of x. Do you agree with that? So what's going to be the big R of x? Okay, here your axis of revolution is here, but your big rectangle is going to be from here to here. Okay, so you can see that what's going to be your top situation here. Your top situation is going to be the 3, okay, of the big rectangle that you have here. And your bottom situation, okay, is going to be this one, which is the parent function, quadratic function. Do you see it? Now, on the small one, it could be any rectangle from here, okay, to the top. Do you see it? It could be this one or something like this. But what you can see is that the top is going to be 3 and the bottom is going to be the 2x minus x squared. Okay, so you can write it like this, so it's more user friendly to you. Okay, so when you have like terms here that you do not have, okay, because that's going to be 3 minus 2x plus x squared. Let me zoom out so you can see the whole thing. You have that this is your little r. So now let's set up the integral here. You can see that the volume is going to be equal to pi integral, and then you have big R, okay, which is this one, square minus the small r, okay, and then square. Okay, so you square this, put a big parenthesis dx, and then you're going to tell me what are going to be the limits of integration. You tell me what are the limits of integration here. The limits of integration are going to be from 0 to 1. Okay, why? Because we're working with x's. Okay, if you were working with y's, then you would be having the y values, but here we're working with x's. That's why I put the big variable there, so you know which one to use all the time. Okay, once you expand it and everything, you have that this gives you 5 pi over 3. Okay, and this would be units cubed, in case that you are wondering, but it's only taking the integral of a polynomial. Okay, so I hope that you find this video helpful. Bye.